Hey, welcome to Everyday Primes. I'm David, and today we're going to do an introduction to prime numbers. Okay, here we've got some prime numbers, 2, 3, 5, 7, 11, etc. There's an infinite amount of prime numbers. These are just the first few. By definition, prime numbers are only divisible by themselves and 1, not divisible by any other number. How do you find out which numbers are prime, you may ask? Well, the oldest way and most tried and true way is the sieve of Eratosthenes. Eratosthenes was a Greek mathematician born 276 BC. So let's do a quick sieve of Eratosthenes right now. The first thing you do is you list all the numbers from 1 to however far up you want to find the prime numbers to. I'm just going to go to 50. The first thing we do is we cast out 1. 1 is technically not a prime number. Then you move on to 2 and declare that a prime number. Then you proceed to delete every multiple of 2. So I'm just going to go down and delete every other one. That's every even number. Then you move on to the next number, which is 3. You declare that prime, and then you do that whole process over and over. Alright, so multiples of 3 would be 6, which is gone, and then 9 would be the first multiple of 3 that you see. So the square of the prime is the first one you're going to find to delete. So we go delete, 1, 2, 3, 4, 5, 6, delete, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6, and we're done. So our next prime is 5, and once again we're not going to find a multiple of 5 until 5 squared. So if you come down here to 25, go ahead and delete that, and then 35 would be our next one. 5's easy to see in the decimal system, and then we're good. That we only had to delete 2 there. So it starts going faster. Okay, our next prime is 7, and we're not going to find another multiple of 7 until 7 squared. So that just happens to be the last one on our list. We delete that. So if we go to our next number, 11, declare it prime, and try to delete its multiples, they're not going to be there because it wouldn't start until 11 squared, which is 121, and that's off of our list. So what we're left with are all the prime numbers up to and under 50, which is what we started with. One cool thing to notice is that 2 and 3 are the only prime numbers that are right next to each other. They're just one apart. All the other primes have gaps between them. So if you look at these gaps, they may seem kind of random. And that's why you may hear people say, oh, the prime numbers are random, or they feel random. And look, here's a bigger gap right here. As the numbers get really big, you go farther down the number line, some of these gaps get huge, and the prime numbers seem to be getting farther apart. But then you'll always find numbers like this, 29 and 31, and they're exactly 2 apart, and we call those prime pairs. So now I'd like to show you why you get these prime pairs and an alternative way to look at the prime numbers and all the numbers in general. Typically when we visualize the prime numbers, we do it in the decimal system because that's what we're used to. That's how we count. That's how we write the numbers, you know. But there is a better way to look at them. If we instead viewed numbers in a base 6 system as opposed to a base 10 system, we would gain some advantages. For instance, in a base 10 system, you always know when something is even or divisible by 5, but you don't necessarily know if something's divisible by 3. And by switching to a base 6 system, 3 would become kind of like 5 in that system. You always know when something's divisible by 3 and 2. And then 5 would just become one of those other prime numbers that are bigger than 2 and 3. Without switching number systems just yet, I've kept this decimal here on the right. I've labeled the multiples of 2 and 3. So everywhere 2 is a factor is every other one, every even number, right? And here's multiples of 3. So every third one, 3 is a factor. And you'll notice that every other 3 meets up with 2 in a multiple of 6. So we got 6, 12, 18, we got 24, 30, and so on and so on. So you get this nice repeating pattern here. And in between every multiple of 6, you can see we have this blank, 2, 3, 2, blank. And another way to look at that is on either side of multiple of 6, you have blanks. And these are the only places that new prime numbers can go. And that's why there's prime pairs. And even when you get way far out into the number system, you still find these prime pairs, because that's where any new primes are going to go. So to wrap things up, I wanted to show you what it might look like if we did switch to a base 6 number system, and where the primes would lie and what kind of patterns we would see. This comes from a game board that I made for my game Man Home, which is a dice game. And here's the link here. I'll put it in the description, and you can check it out, play it, or download this for yourself if you like. So the number line goes up and to the right here, and it's still in decimal, but the layout is in 6s. So we get to see the patterns of the primes here. And at the very bottom, you see that pattern I was talking about. Here's 2 and 3, blank, 2, 3, 2, blank, and then that repeats. So everything in this 3 column is in fact divisible by 3, and everything in the two columns here, they're even numbers, and they're all divisible by 2. And under the 2 and 3 column, well, those are all multiples of 6, so they're all divisible by both 2 and 3. And the 2 blank columns, well, that's where the rest of the prime numbers go, because it's the only place they can go. So it's nice to have them organized into these columns. You got 5, 11, 17, etc. going up this column, and then 7, 13, 19, 31 going up this column. And you can see that extend as you go up the board. Alright, that's all I wanted to show you in this video. In future videos, we'll go into more detail about this Senary layout and prime numbers and their special patterns and properties, and we'll get into it and have some fun here on Everyday Primes. Thanks.